artifacts produced by a software process, which are requirements, design, implementation, test cases, and documentation. You can just go down the list of the software process steps, and for each one you write what is being produced.
We don't. Well, do we define each of them, or do we
No, just list them.
Okay.
So for this question, you just list each one of them. You know,
Okay.
say, the answer would be like, software is all artifacts produced by a software process, which are requirements, design, implementation, test cases, documentation. That's it.
Well, that was intro 2.
Oh, intro 2. Yes, intro 2. Sorry, I said the first one does not present. Intro 1, actually I do not present, so just remove it. Intro 2. In the same place, there is a definition of software engineering. So it's the same slide right here. Software engineering, the application of scientific knowledge to the development and maintenance of the system. So one thing is that remember that scientific knowledge, why I told you before, is that because we want to be able to write algorithms that analyze other programs. So we want to be able to represent software in a formal way and write algorithms that find out something about it. Like, do they have does the software have a possibility of deadlocks, or does it correspond to some specific requirements, so on and so forth. And second thing is that it's not just development, but also maintenance. Because maintenance takes much more time than development. Yes?
So the list you mentioned, is it that development, operation, validation, and maintenance? Is that the list you were talking about, or is it the EG thing below it?
Which list do you mean? So the first question?
You said for that question you wanted a list.
For which one? First or second?
That's the first one.
For first question. A list of them. Yes, this list.
That one.
This one, yes. This talks about artifacts to assist with, but doesn't enumerate the artifacts. And these are the artifacts which are part of software. Okay.
All of those? Or just
Yes,
most of them? Because
you don't need to remember all of these. No. The ones that I mentioned are the ones that correspond to main steps. This just goes along the list of everything that can potentially be produced during software process. Imagine that waterfall software process, which you should know anyways, and write an artifact for each one of them. That's the basic stuff. Everyone should remember that thing after taking software engineering course. Requirements, design, coding, implementation, implementation, test cases, documentation. Alright, so the second question I just described, this definition is very, very simple. Then goals of software engineering. So they're in this set of slides, but lower, let me just look for them. Let me press Control F, and I'll type in goals, and here they are. Improve productivity, improve predictability, improve maintainability, improve quality. So this is this question 3. 4, yes.
Sorry, 1 second. Question 2 was the GESI definition.
Question 2, actually, that was Mary Shaw's definition. GESI definition is on the second slide.
Yeah.
So this is GESI definition, and this is a definition of a professor at Carnegie Mellon, Mary Shaw.
Okay.
Sometimes I show it, but Mary Shaw also has a namesake who wrote Frankenstein. So sometimes she shows up here instead of the poem.
Wait, isn't it Mary Shelley?
Very showing.
Mary Shaw,
But
but it shows up
Intro slides.
Mary, yeah. But the Google associates them somehow. That's the Mary Shaw that's her definition. And that some folks, that's what I was taught myself. I saw these slides back in 1996, maybe in 1997, this one. So. Okay, so then peculiar properties of software based on the silver bullet paper, and right here they are enumerated. Now I do want for you to give a description for each one of them. So for instance, complexity. Software is much more structurally complex than other artifacts. For instance, because it can change its structure during runtime. Conformity. There is no baseline to compare software design to. Changeability. Very small change to software can lead to great deviation in behavior. It's a great deviation in behavior. And invisibility, software is intangible. So we don't know how best to represent it.
What did you say for complexity again?
Software has much more complex structure than other artifacts. For instance, because it can change its structure during runtime.
Wouldn't that be more in line with changeability?
No, changeability. By changeability, what the paper describes, what he means is the fact that you could accidentally introduce some small bug or something, and behavior could be vastly different. That software has this, unlike some other artifacts. That's what he means by changeability. Not like ability to change or how easy it is to change, but the fact it just blows up from a touch. You know? That's it. It just explodes from a little one thing. Change a bit somewhere, it can potentially behave vastly different. The next one, also from the paper, difference between essential and accidental properties of software. So he does go on for quite a bit there in the paper about what they are, and I think that a good succinct definition would be for essential properties are those that capture a computational solution. Essential properties, those that capture computational solution.
So like a function is an equation?
Your algorithm, your structure, whatever you're using, the structure of your system, the algorithms that you're using, they capture the computational solution. If the language would just define those, say programming language, it's fine. And accidental properties are properties due to the state of the art. I'd say current state. For instance, pointer arithmetic is accidental property. Take a look at C program. Someone's manipulating pointers there. This is not essential property of the computational solution. This is accidental.
So, do you just want the definitions, or do you want examples too?
Just definitions are fine. You can give small examples if you want to, but just definitions is fine.
And you said accidental was the...
Properties due to the state of the art.
So there are things that we found we can do because of the way that particular language operates, basically?
Can you elaborate on that definition a little bit more?
So, for instance, what pointer arithmetic, right? So for instance, there is something that programming language contains, not programming language, like software system written in some programming language, right? Contains some code that deals with our current ways of doing computation. State of the art. For instance, we have currently And imagine, it's easier to imagine this way. If we take code that's written now and would like to write a compiler for it in, say, 2,000 years, how much work we would do to do that? If you take C program that heavily uses pointers, or any of them I guess do, right? In 2,000 years, you take that program and you want to write a compiler for quantum computer. How much you'd have to change? How much in it captures the actually implementation of the algorithm, binary search, whatever, that decides how data manipulated, as compared to something that just deals with the machinery it runs on. Does it make it, does this analogy help anyways? Like by state of the art, like current state, what we know. So, for instance, Turing machines are not likely to change. Turing machines are abstractions by itself. They capture computational solution to the greatest degree. They don't refer at all to like pointer arithmetic or anything of that sort. They're not even bound by binary per se. You don't need to use binary for it. But they're just too abstract, I guess, for everyday use. They're very abstract notion. So, so that's what's meant by accidental. So something that you had to do just because right now that was the state of the art. Or some other analogy, yes?
So what would be an example of an essential property?
The structure of your system or the algorithms that you use. Software system, your software system. So that's why that author was making a point, is that design is most important, more important than the implementation. Because design shows how you created the structure of the solution.
So would you say that that's a one-to-many relationship? You can have one design and many different implementations?
Yes, definitely. Yeah, I even mentioned that before. Very many implementations. And the thing is that there is a strange argument about how it would be infinite number, just like about implementations, because as long as part of the system computes what you need, it can do the infinite number of other things in between. So that's why they say there's an infinite number of implementations of something, of some requirements.
So then an essential property is, for instance, the way that the calculators in the 80s used to find, say, I don't know, the E number, as opposed to the way they do it now. Because they're operating on different, they're utilizing different software inside each machine, but they're doing the same computation with the same algorithm. So that would be an essential property?
Is the algorithm
Yeah, the algorithm's the same. It hasn't changed since 2,000 or 3,000 years ago whenever somebody
well,
started.
it's a series, right?
Yeah.
So it goes into a series. So the algorithm would be essential in this case. Yes. Now they might be different ones, right? You suggest one essential solution, someone suggests another one, but as long as not tied to whatever it runs on.
Yeah.
Right. So, for instance, before we had electronic computers, it was very important to know how to operate mechanical computer, for instance, right? Or before we had electricity, if you wanted to light a room, it was very important to have like oil, right? Now, if someone asks you, light it up, let me go run get oil. Like, no, it was accidental. It's not essential right now, so just go get like an electric light or something. So that's kind of an analogy to it. And for software, once again, I think that if you would think like a compiler that would be able to run some program in million years, maybe even, that simply captures how the data are processed. Yes.
So an essential property, so an accidental property you could replace with a newer way to do
Exactly,
it, but
yes.
essentially you can't.
Essentially, you can't. No. Exactly. So, for instance, you got an efficient algorithm and you prove that's an efficient algorithm for a computation of something. You cannot find more efficient one in a million years. It will not work. So that's what essential property is, like the algorithm and the structure. Okay, then examples of solutions to software development to describe why it is not a silver bullet. And I gave two examples. So basically, the idea is to show if there is some method does allow to create, to help, to improve, to do less work in one of the steps, it creates more work at some other step. The goal was to create a method that would improve by the order of magnitude something, reliability, so on and so forth. But such methods are not been achieved. Every time some method is suggested, it also has a drawback. There were two that I mentioned, object-oriented and formal verification. So, object-oriented, very briefly. Object-oriented approach introduces software reuse that improves, increases the speed at which software is developed. But it introduces the need to create a class diagram, at the very least. And time is spent on that, additional time. And for formal verification, so formal verification allows complete automation of checking properties, but someone needs to define properties formally, and now they have to take time in that. I believe for both cases, I mean, the paper has sections, so you could look them up, but these are very short summaries of. And that's enough, a couple of those pretty much. So it's like, compare it to like a ball, the volume stays the same. You think that you just pressed it on both sides and the projection looks like it has an oval shape, one of the radii is smaller, but the volume stays the same. Then next, be able to describe the difference between functional and non-functional requirements and give examples. Functional requirements focus on mapping between input and output. And non-functional describe various attributes. For instance, performance, reliability. You don't describe input-output mapping.
So you would say non-functional requirements are more of like a intangible?
Well, functional also intangible. In the sense that data are described using mathematical notation. You could use set theory to describe data and logics to describe constraints on them, and those are also intangible. But it's in the sense that they don't describe the constraints on what output represents, right? It doesn't say that, for instance, we want a program that sorts elements, right? According to something, maybe sorts integers in increasing order, right? A non-functional requirement would not describe that we should have an array such that each element AI is less than element AI plus 1. It describes what the output is. But it might describe, we want to know to get it done in linear time. Or like in under 5 seconds for this computer, I want to be able to do that for arrays under 100 elements. Or I want to have reliability of that program that computes for me the increasing array, 6 months without failure. It describes, it's an attribute of that. It doesn't describe what's being produced, but how fast, with what reliability, and so on and so forth. And we talk more about that over. Maintainability, usability, so on and so forth. They all describe these attributes. Then be able to describe software qualities, give examples including possible metrics. So really, I care about the first three, that's what they usually give. Not all of them have metrics. So what is correctness? A correspondence of a software system to requirements, and it's a yes or no notion, as we went over at length. So there is no metric for it. You cannot say that something is 50% correct or whatever that is. It's in relation to properties. You might have missed some properties. Change a set of properties, it would become incorrect or correct in the end. But briefly, a correctness, correspondence of software to requirements, and there is no metric. Reliability, an ability of the system to function reasonably under expected contingencies or circumstances. One possible metric is mean time to failure. There could be many others.
You said correctness is just if it meets the requirement.
Yes.
Okay.
And remember, I went at length when I was describing it what actually it means in practice. That you write out properties that are important for requirements. You are not sure if it's all of them or not, but for the set that you have, as long as the software corresponds to each one, it's correct. You might set changes. Maybe you missed some important ones, so on and so forth. It still would be considered correct because these are the properties. There's a number of them. And the software system verifies for each one and does expected output. Okay.
So reliability is a non-functional requirement
Yes.
as well as a quality?
Yes.
Okay.
So its ability to give correct desired output with a certain probability. It's pretty much, it's like probability assigned on it. Like I expect the system to give me the desired, the ones that I expect output 90% of the time, like in 6 months, for instance.
Would
Yes.
all of the primary software qualities fall under non-functional requirements, with maybe the exception of correctness?
Yes,
So, but correctness would need to be a functional requirement.
functional
right?
requirements,
Okay.
yes. So for instance, your scenarios, a high level description of your requirements are your properties in a way, because you describe how you expect the system to behave in response to input. As long as the system does exactly the same on all inputs, it would be correct, except for you cannot check it realistically, because then you have to do exhaustive testing, because you actually will have to plug in numbers from time to time or strings.
And can you give us, so correctness, reliability, and robustness are the three primary qualities? Can you give us a definition?
Performance, also performances, but I'm not asking you to give examples of performance.
Can you give us an example of robustness?
So robustness metric is time to reboot. Time to reboot.
Robustness is the ability of the system to perform under unexpected.
Under unexpected, yes.
Okay,
And
so
robustness is the ability of the system to perform under unexpected contingencies.
So reliability is expected. And
Expected,
and
rel-
robustness is
unexpected,
Unexpected.
yes. We also had a lengthy discussion about what I
Yeah.
mean by that. So, but I don't ask you to give it. And once again, only software engineer researchers seem to be. What's up with that? Oh, they finished.
Okay.
Okay.
I guess.
Tonight we'll be closing at 5 p.m. All votes will be checked out by 4:45 and the circulation
All right, so only software engineering researchers seem to care about this distinction between reliability and robustness. Normally, they don't separate them. And so for robustness, I mentioned very simple general metric, time to reboot, because imagine, no matter what happened, it's not going to investigate what happened, just reboot to the previous state. Let's hope it doesn't crash again. And there are also problem domain specific metrics that could show up that usually relate to, when part of the system is destroyed, it's still able to do something. Part of the hard drive is destroyed, some sensors are knocked out, it still can do something. Maybe some part of the actuator of the robotic arm is destroyed and it still can do something. So all those, or can do something, can accomplish the task to some degree, whatever it's supposed to do. All those would fall robustness, and it's possible to assign numbers to those too. I said that these are most important. Besides these, performance is also very important. I did not put it here. I think it's because it's very easy. For performance, you could always come up with stuff. Throughput, response time, so on and so forth. Performance is very important together with these. Quite often it's implied. Folks don't necessarily mention it in requirements, especially for some systems that's just web services and so on and so forth. But if it's a control system, they would mention a lot of that stuff.
So we're not able to hear the questions in Round Rock. Can you push the button?
That's for.
Yes. Oh, okay. But there was, I don't remember what was the most recent question. I was kind of going on by myself. Yes, but we'll remember to do that, to press the button as I mentioned. Okay. The questions were about whether, so one of them was that correctness is the only functional requirement out of all this list, that yes, it is. Then there was a question about what would be the metric for robustness, and I mentioned the general one is time to reboot. Difference between definitions, reliability, robustness, reliability, ability of the system to function reasonably under expected circumstances, and robustness under unexpected circumstances. Behave reasonably, very general term too, but it's enough. So you could imagine what you would like system to do. So then, and quite often I ask some question to give examples of reliability and robustness property that you could give. So for reliability, you could tie something to mean time to failure, for instance. For robustness, you could mention maybe an ability of the system to function with 50% hard drive destroyed, for instance, or some sensor network to be able to provide updates on targets with up to 30% sensors destroyed.
That's robustness.
Robustness, yes. Yes.
What's performance?
Performance is an important property too, but I do not. Yes, you should put in the button.
There really is no button right next to me.
Oh.
I see one anyway.
It's the closest one.
Yeah, yeah.
Just press a tree, you can hear it.
Yeah, so what's performance?
So performance is a non-functional requirement, and performance itself can be expressed under different metrics. For instance, response time, throughput, and scalability. So, next question, very easy, next two questions, because I give answers right there. So, describe the emphasis of requirements document, emphasis on what, not how. Major qualities, requirements should be complete and consistent. Yeah, this question I think I won't have. Be able to write a short requirements document. Okay, I will not be asking about writing requirements documents. Then the notion of a software process and why it is needed. So a software process is a set of steps and execution constraints. It's a set of steps and execution constraints. Why is it needed? Following a process increases the qualities of the system.
You should say it builds in the qualities.
Builds in the qualities, yes. Following process builds in the qualities or increases the qualities. Builds the quality into the system. And intuitively, remember, I don't have to mention it. I described that it just introduces a number of intermediate steps from requirements to code, and as correctness is defined, correspondence of software to requirements, you are less likely to deviate.
Sorry, could you explain why it is needed?
It is needed because following a process builds quality into software. Waterfall software development process is described in the same set of slides that intro to. Remember, there was that diagram. Where it is? Where is it? Right here. So for an answer, just want to see this diagram with very short description what happens in each stage. Requirements are produced. Design is created based on requirements. Implementation is created based on design. Testing is done to implementation based on requirements. Maintenance, a system is changed and retested. Yes?
Do we draw the picture out or we?
Yeah, I prefer if you have a picture, but you could do it just in a line. I mean, in a what? In a line, in a column, like one by one. Requirements and so on and so forth. Occasionally, I mean, most people don't have any problem with it. The only difficulties might come if someone omits something important, like you forgot testing, for instance, or you forgot design completely. There are so few of them that's hard to do that. Of course, everyone remember requirements and implementation, as I noticed. So that's the only way to lose any points on this thing. Yes.
And that's the same list you mentioned earlier in the first question?
Yes. The first question for software. So, but the difference is that that list is about artifacts produced by these steps. Right? So, this one, for instance, has testing, coding, and in that list you would have like code and test cases, because that lists about what they produce. Then, definition of an agile software development process, and conclusion from that paper is those 4 items. In the conclusion, remember, it's incremental, straightforward, adaptive, and collaborative, I think?
Cooperative.
Cooperative. Let's see. Right here. This conclusions, these 4 items right here.
And are you gonna want a small description of each one of these?
Yes, that would be good. Yeah. But this is just this 4 items, very short answer. Actually, don't be difficult. describe XP process diagram, and that's the diagram from, let's see, where did I have it open? Oh, right here. So let me do screen, and page 18 process right here. Oh, it doesn't go.
You get to scroll the old-fashioned way.
Hit the down arrow key on the search.
But I just, oh, here it is. So it's this diagram. What's important primarily is that first we have scenarios, then we create iterations, then there is a single iteration that contains pair programming and pretty much some version of the process right here. That goes, and goes. So those are the main things. And we could mention these two, but the status.
So we just need to know exploration, basically,
Oh.
iteration.
Yeah, you could, exploration, planning, iterations, yes. You could mention the rest of them too, but this is the main things. And the fact that there is pair programming. So this some static analysis is done, informal static analysis. And many folks associate pair programming with extreme programming quite a bit. Pretty much very similar diagram could be done just pretty much for any incremental process. They do have a bit different diagrams for other agile processes here, but it's very, very similar. Then there is a question about advantages, disadvantages of that one. Big advantages, disadvantages. So for advantages, you could mention timeliness due to incrementality. Timeliness means by deadline for the project, you definitely have some functionality implemented and tested. Tested is important, too. Some folks just write code, it compiles, it runs for some very short, few test cases, but when you try to use it for something serious, you notice that it's very wrong. Probably they tested it for like 30 minutes, making sure that it doesn't crash immediately.
What would be a disadvantage?
And disadvantage, because of regression testing, for large systems, once system becomes like hundreds, thousands of line code, it starts sucking up time on regression testing.
So the advantage was timeliness, but the
Timeliness of
disadvantage
creation.
was.
Its timeliness of creation is the advantage, disadvantage is the timeliness of your testing.
Timeliness, by timeliness we mean that the fact that it can, by the deadline, it will have something, some functionality implemented and tested. Right? So you will, by this process, you will not be empty-handed, so to speak. But disadvantage, regression testing, takes a lot of time when the system is big. Over 100K, it's already pretty big. Remember that regression testing is that retesting, right? Retesting. Code base is large, increment is small, you still have to retest a lot. You do many increments, you happen to be retesting quite a bit. So the next question, that's the one that I did not mention before. Let me write this out. These are very simple ones. Nothing too difficult. Let me switch to Elmo. Elmo, where By the way, I myself don't see the list now.
It should be from
No, I mean I don't see the list because there was a list of those things.
It just says,
Modules, objects.
Library data.
module, library, data pool, object, class,
Okay,
interface. and
let me
type.
write it down.
First one's module,
Uh-huh.
second one is library, then data pool, object, class, interface, and type.
Okay, so most of these come from that book by Gezi, and a few, there is a book on unit testing for Java. And most of these are these module, library, data pool, and object. And they also relate in this way. Let me write like that. So there's module, library is a kind of a module. I'll write what it is. Then data pool is a kind of a module. And object is a kind of a module. Object. Class is a kind of an object. Okay. So a module is a container for either attributes or operations or both. Say contains attributes and or operations. And the first modules were just subroutines pretty much. Like, for instance, in Fortran. Before that, I guess there was something too. Algol, some other languages, old ones. One of the first things that folks thought about is just to break up the code into subroutines. Oops. Then libraries. So these I can define via module. So it's a module that contains operations. Now data pool is a module that contains attributes. Now, object is a module that contains, and here related attributes and operations. And operations. And a class is an object. So, see, so now class is defined in terms of the object. Objects with a constructor operation. Or there could be several of them too. Constructor operation. And then interface. A set of function declarations. There are synonyms for function declaration. There's a function signature, for instance. Sometimes you see in literature. So interface is independent of implementation. Now, possible to define type in different ways, depending what you mean. No, say depending. It's the same meaning, rephrased different ways. But one way to say that type is a set of objects that satisfy the same interface. A single object can satisfy multiple multiple interfaces. Sorry.
Is there a difference between type? Is there a difference between type and primitive types?
Yes. So here I'm talking about objects. For primitive types, it would be just a set of elements that share some property. So I could write for primitive type. Yeah, because like integer, for instance, so on and so forth. Those, in some languages they are objects, but in many languages they are not objects because they don't have operations, just memory for the value that has certain interpretation. And that's why I mentioned that type. But generally speaking, type is a set. They just have the same meaning. Type is a set. Primitive type, we could say, primitive type is a set of elements, I would say, that share the same properties, some properties. Those are the properties that define the type. It so happens, as I mentioned, that type in object-oriented languages, for instance, is determined based on the language. So in Java, a type is determined by its class and the set of interfaces. Essentially, you're looking for what in the language would help you understand which operations an object provides. Java has single inheritance and allows an object to implement multiple interfaces. So, complete picture about operations that an object is providing, I'll get when I know its class and all interfaces. Then I will know that. If I have some language that has multiple inheritance, then the complete picture would be provided by the set of classes from which it inherits an object, about all operations that it can provide. But it can have multiple types, so that is the set, like the closure of it, right? And all the closure includes all the subsets, all the types that it could potentially satisfy, which is just all the subsets of the operations which it implements. So this is that, right? Yes.
So class is an object with constructive operations?
Constructor.
Oh.
Constructor. It's a constructor. That's what makes it a template for instances. And there could be several constructor functions also for a single class. So this is the programming language view of what class is. Because quite often you hear things like class is a template for objects, where they don't make that distinction. Let's say the object is just attributes and operations in memory. Class is also an object. Attributes, operations in memory. But it has constructor functions. Instances don't. That's the difference. And that's from that book by Benjamin Pierce, for instance. But also a lot of other programming languages folks share that view. The ones who work in the area, who research about new programming languages, so on and so forth. Okay, so that's the answer to that one. And of course, no, I don't ask give me this whole thing. I might ask, what is an object, or what is a type? And that would be enough. So, you see that type and class are different things. Type doesn't encapsulate implementation in any way. Class exists so that to provide implementations to others for inheritance. But quite often we do it interchangeably because in languages we use the name of the class to declare the type of a variable and we write it. array list, for instance, in Java. Oh, it's type, but it's a class. Well, it's type also. Okay, so let's switch back. And yeah, we'll finish on. All programming, according to Strauss, means programming with inheritance. Object-oriented programming means programming with inheritance. In other words, that means that you use inheritance in your code. This means that you could use object-oriented language without inheritance, and it will not be an object-oriented program. Don't inherit single class. Don't use it. So, languages are just tools that can help us do stuff, but they don't enforce us to do it in some way.
That's the only property we should be
Yeah, for
concerned
this
with.
one, yes. There are many other definitions and so on and so forth, but at least this one is good. I think he developed C++, right? C Stroustrup?
Yeah.
Bjorn Stroustrup, yes.
Are we required to elaborate on this or?
No, just one single.
Short and sweet.
Yeah, object-oriented programming means programming with inheritance. I used to have a reference to one of his papers in which he just gives it at the very end. I don't remember if I still refer it somewhere, but it was very short at the very end. Okay, these principles we just gone over, and I will ask, a few of them. Most likely I'll ask those three that are the most popular. Encapsulation, polymorphism, and what else is there? Inheritance, yeah, or inheritance.
Or association.
No, inheritance. And for each one of them, give some description what it is. So that scan gives you an idea about it, and also we did describe it just recently. Remember, encapsulation is hiding object state. Polymorphism, an ability to provide multiple representations for a single function declaration. Inheritance, an ability to inherit behaviors. Behaviors, a more general term for implementation.
What was inheritance again, sorry?
An ability to inherit behaviors. Actually, it's also an ability to inherit the attributes by type, but that's the most important. There was a comment? No? Could you press again that button or do some?
Do we not need to worry about those other two? The ones that aren't encapsulation, polymorphism, and
Subtyping,
inheritance?
open recursion.
Yeah, I remember those. Well, I think that it's still reasonable to read about them. Yes, I might ask subtyping. Open recursion is a bit too complex. So subtyping, an ability to provide a type hierarchy. So that one is very, very simple. Then, this question, I sometimes prefer that students themselves try to describe based on what we talked about. Why is it important to specify and analyze software design before implementation, especially for large software systems? So we talked about model-driven approach, and I was mentioning something along those lines. Like before you write code, especially if your system is going to be large, why do you want to define design and then analyze it against requirements? How does it help?
It gives you a structure to use, time saved, you can do things in pieces.
Time saved. So the main thing is that it's supposed, well, the main thing, tangible one, it will save on testing. It will drastically reduce time on testing. Why? Because each feature of the design is mapped onto many, many features in the code because it's very abstract, right? Something abstract projects on a lot of lines of code that implement it. So, if you detect a deviation in design and remove that deviation, you remove like hundreds of bugs that otherwise would be in the code. So you prune it from a lot of possible hundreds of bugs on which you will not be spending time later. There will be some bugs there anyways. But if you verify the design, analyze it against requirements, then you will have fewer bugs. You'll save on testing time. And there are other of course benefits for it, so it's possible to come up with something else, but this one touches on the bottom line very much so. Then development process from the textbook, actually that's the one that I drew, and the textbook does not contain that diagram, but it's a very simple one. Right. Remember I drew the diagram here. So if you could recreate that one.
So like regular system, initial class diagrams, class
Yes,
diagram.
yes. So it branches out. One branch goes into structure, which is class diagram. Another one to behavior that goes use cases, scenarios, sequence diagrams, state chart. That's it.
You wrote more than that.
Yeah.
Yeah, I introduced different sequence diagrams,
Yeah.
I introduced like base sequence, system sequence diagram, subsystem, so on
No,
and
we
so
only
forth.
need to know those basically, but 5
Yeah.
main ones.
And yeah, that one is tied to UML because it was by Grady Butch. Their object-oriented processes are not tied to it, but this is easier thing to understand. And generally speaking, object-oriented process, just like many other ones, is about how you create design from requirements. They don't necessarily even care about how implementation is done. It's about step from requirements to design, how you create modules and how you connect them. Then we did not speak about use case diagrams, so everything relating to use cases will not be asking. And also about sequence and state chart. Yes, so all of this will not be there. From class diagram portion, well, there will be a problem that will give a short 1 paragraph, 2 paragraph description of requirements, and you will be asked to create a class diagram based on it. So we'll do an example of that on Monday, where you'll have to write out the nouns from the requirements, from that 2 paragraphs, create classes based on them, create relationships that we talked about, inheritance, segregation, association between them that are reasonable, and then populate the class descriptions with attributes and operations. You will not need to say to provide types for attributes or operations, just names what you think is reasonable. The 2 problem domains that are quite often used, one is a library control system. So that one keeps tracks of, say, books and journals and folks who subscribe, members of the library, or the gas station, where we'll have nozzles, pumps, fuel grades, what else is there? Cars, transactions, and something else maybe, I don't remember what else, but those are the main entities in that thing. And say requirements for a gas station are on tracks. I modify them a bit because especially in this problem, I tried to be very specific so that it would be easy to create a class diagram, so that there would be very few ambiguities. So the description that you will see on the midterm will be different than that one. So that is an example, but it will be different to make it easier, to make it more straightforward to create diagrams. Like a English language description that you get almost one-to-one maps onto a diagram. So, in description and tracks is gas station requirements like this one. And got to use cases, technically the whole requirements is here, summary of system requirements. That's it. Okay? So, it's not that difficult. And by the way, in relation to this example, there is also, even though I don't quite like it, how they do relationships, there is a class diagram that they suggested for it. You see they have associations almost everywhere, just one example of generalization, no aggregation. But you could see that's an example. And I'll be talking about it more during our example, for a class diagram. But I always mention, remember to include the main container class. You have a gas station, there's going to be class gas station that refers to other main things. You have a library, there's main class like a library that refers to the rest of the things, like has arrays of books or whatever that is. And remember that also there are classes for individual items and for sets. So some folks read in requirements it says books in the plural, always. And they dump in a class called books. Well, there should be a class book, single, one. And somehow they don't mention that or omit that. They also could have class books, would have different functionality. They might not need class books, they would just have some, again, array somewhere but a class book would find its way there somehow. So remember about this fact that if the requirements don't mention something in the singular, it doesn't mean that there would not be a class in the singular. And there should be like main container class. Okay, so these you can take a look at. Then that's it. That's it. So you could ignore this use case sequence stuff, and for a class diagram, I'll be asking that example. You will not need to describe to me what a class diagram language is. You just need to apply it. All right. So let me stop here now. So on Monday, then we'll do that example. Maybe on Tuesday, I'll let you finish up your SRS, for instance.